Okay, guys, let's get started. So I uploaded homework 2 today, so that will be due on next Monday. So yeah, it's relatively straightforward. I only have 6 questions. And let me know if you have any questions. So I will probably upload lab 3 by the end of today. And so if you finish lab 2 already, I see some of you submitted lab 2 already, so you can take a look at lab 3. So which is also relatively straightforward, but you need to use the software-defined radio dongle for it. All right, so yeah, let's review what we covered in the last lecture. So basically, in the last lecture, we focused on the demodulation, and in particular, we focus on the magnitude, the magnitude modulation. Okay, and so we consider the simplest case, which is a message signal multiplied just by a cosine, right? And then we add the carrier signal into it, right? So if we do that, so we have 2 conditions, right? So we have 2 cases to consider. One case is a plus mt is bigger than 0, and the other one is it is less than 0, right? And as we said, so if it is this quantity is bigger than 0, it basically means that all the signals are above 0. So we say, okay, there's a chance that we can detect the envelope, right? So hopefully we can see how can we do that exactly today. Yeah, and based on that condition, so we can derive it. So basically, A has to be bigger than or equal to MP, where MP is a range of MT. Right here should be a minus sign, so I missed. So yeah, that's basically the condition. And based on this, so we have a definition. It's called the modulation index, so which is defined by MP over A, right? Where A is the magnitude of the carrier, and also this MP. So that is basically the range of the message signal. Okay, and okay, so yeah, so we're gonna probably use that later today. And so based on that, so we have 2 concepts. So the first one is that when mu equals to 1, we said signal is 100% modulated. If mu is bigger than 1, we said the signal is overmodulated, right? So which is not good, right? Because in this case, so we cannot use our envelope detector, okay? So then, given this AM signal, and so we want to see whether it is power efficient or not, right? Because we need to transmit the carrier together with the signal, right? So yeah, in this case, we may lose some power, okay? So in order to determine that, we define a concept called power efficiency. So basically, the definition of it is we use the useful power, which is the signal power, divided by the total power, which is the signal power add the signal power as the carrier power, and then we multiply 100%, okay? And we're going to see how we compute that today, so which can be troublesome, okay? And for simplicity, we'll assume that our message signal has a 0 DC component, which basically means that the integral of our signal over time is equal to 0, okay? So yeah, that can simplify our life a little bit, okay? And so basically, this is the signal that we consider, right? We have a carrier component, and we have a message component, right? So I want to compute the power of this. So this is the basically the total power, right? So so the power of this guy is the signal power, okay? So we're gonna use the power of this guy divided by the total power, okay? So that's basically the idea to compute the power efficiency. And in order to compute that, so we can decouple it into 3 parts, right? So this the norm of this guy, the norm of this guy, and then we'll have inner product of this and that. Okay, so here, so we slightly abuse the notation a little bit. So this norm doesn't mean just the norm we defined before, right? So norm in the power sense, right? So basically, we need to integrate it, over minus t half to t half divided by 1 over t, and then let t goes to infinity, right? But all the property of the norm will still hold here, okay? So just for a simplicity of the notation, as we're gonna see later, okay? And so in order to compute it, we can see that. So this part is easy to compute, right? So you can just try it offline. So basically, it's a periodic signal, right? The only thing we need to do here is that we will do an integral of this guy squared, right? And then the range of the integral is just one fundamental period, and we normalize it by the length of the period, right? So we can see, so the value of this is just a over 2, okay? So you should be able to do that. So in your homework 2, you're going to compute the power and energy of a signal, basically, okay? And this and that can be harder to compute, right? So basically, now we're just focused on the computation of this and that, okay? So this is where we arrived in the last lecture, okay? Very good. So any questions so far? Okay, so let's see. Today is our lecture 14. So we'll still talking about the demodulation of AM signal, and we're going to focus on 2 components. The first one is the power efficiency. And the second topic here is AM demodulation. We're going to see how we can demodulate AM signal. So be careful here, right? When we say AM, this abbreviation, we basically means the signal plus a carrier, right? So we have a very special meaning for it. It doesn't mean the general amplitude modulation, okay? And probably we're going to talk about this in the next lecture, but I'll give you a head up. So basically, after that, we're going to talk about bandwidth, efficient modulation, bandwidth efficient amplitude modulation. Right, this can be more interesting, right? Because so as we have observed before, and I think one of you asked me this question. So when we consider a real signal, right, it's kind of symmetric, right, in the frequency domain, right? It's kind of only transmitting half of it is enough, right? So that, yeah, in this topic, we're going to talk exactly about that. Okay, great. So first, let's focus on computing the power efficiency, right? Okay, so yeah, let's see. So basically, I'll write the formula down here. So the total power of the signal is that. So we have this plus the inner product okay, and then we add the power of the signal, right? And we said, so the first part is manageable, right? So that's it's okay. So that is square over 2. Okay, so now we're going to focus on computing this and that. Okay, so let's see how can we do that. Okay, we're going to start with this term, right? So yeah, I'll write it here. Yeah, maybe we mark it as second term, and this is the third term. Okay. For the second term, so this, yeah, let's see how we can compute it. All right, it's an inner product, right? So yeah, let's write down the definition. So be careful here, right? So it's not the normal inner product that we've seen, right? So we define the inner product in the power sense, right? So we need to have this dummy variable t here. And mt cosine, right. And then dt, right? So this is what we have. And so this can be combined, right? Have two cosine here, so that equals to a mt cosine square, right? Yeah, looks pretty good, right? So cosine square, right? We know how to deal with that. So we have seen this term many times, right? We just use the trig identity to get rid of the square, right? So this basically equals to the following, right? It's a mt multiply 1 plus cosine 2 omega ct, right? And then have a factor of 2 here, right? So this is what we got. Right, and then we can break this term, right? We can break it because we have 1 plus this guy. So for the first guy, so that equals to amt over 2 dt, right? Looks pretty good. And second term is, second term is amt over 2 times cosine 2 omega ct dt. Okay? Yeah. For the first term, can we compute it? Yeah. Yeah, just this term. Yeah, because we're letting t goes to infinity, right? So when t is very large, then basically that'll give you the DC component, right? Remember, the definition of DC component is defined by this, right? That's the DC component, and we denote that as this, right? And we assume that is 0. Okay, yes?
Can you write what you wrote at the bottom on a different area, because I can't see this?
Yeah, this part?
Yeah.
Yeah, no problem. Yeah, I'll just copy that here. So basically, yeah, because of the monitor.
Yeah.
Yeah, maybe I can put it down a little bit. Yeah, I'm not going to use my computer now. Oh, that's fixed. Cannot do that. Yeah, never mind. Yeah, let me copy that. So basically, this guy will equals to, yeah, let me write down the whole thing, right? So that's limit t goes infinity. And then we have 1 over t. So we have, let's say, this. Okay, and then we add another term. Yeah, this is what we got, right? The first term I think is okay to compute because we have the assumption that DC component equals 0. Okay, so can we compute this? Right? Yeah, probably it's not that easy, right? So I have signal multiplied by cosine, then, so how can we compute that? Right, because we have cosine there already, right? So there's nothing to simplify. Yes?
Why isn't it also 0? Why isn't it also 0 since t is still going to?
No, we don't have any assumption for MT.
Okay.
Right? MT is a general signal. Right? This signal could be even, could be odd, could be whatever. right? Okay. Seems that we have a problem here, right? So any other idea to compute it? Yeah, maybe the problem is, so we started in the wrong way, right? So normally in signal processing or in signal system, okay, so when we compute something in the time domain, so and we cannot continue anymore, then what should we try?
Convert it to the frequency domain.
Very good, right? So if we got stuck in the time domain, so we may want to try something in the frequency domain, see whether that will be easier or not, right? So that is basically the idea. So let's try to compute it in the frequency domain instead of in the time domain, okay? So let's try a little bit. Yeah, because we're computing an inner product, right? Because of Parseval's inequality, or Parseval's theorem, then basically we can do the same thing in the frequency, right? So basically, this guy, yeah, there's no square, right? Why I write a square here? So basically, so this guy, so I will just, yeah, I didn't write the 2 there, right? Okay, so basically, this guy in the time domain, so we can just compute that in the frequency domain, right? So basically it means that so it equals to inner product of the Fourier transform of that and the Fourier transform of that, right? So that is kind of the generalized version of the Parseval's theorem. So we didn't cover this property in class in very detail, but include that in the slide. So if you forgot, you can check slide in one of the previous lectures. So basically, this idea, right? So that equals to the inner product between the Fourier transform of this and the Fourier transform of that, right? So the Fourier transform of that is just the Fourier transform of the cosine signal, right? That's a over 2 times delta f plus fc add 2 over a delta f minus fc, right? Yeah, remember, so for fc, omega c equals 2 pi fc, right? Okay, and then we want to write the Fourier transform of this guy, right? So this is basically our DSB-SC signal, okay? So we have seen this Fourier transform for a few times already. So basically, for that guy, it's equal to half mf plus fc plus half mf minus fc, right? Where capital M is the Fourier transform of the MT. Okay, so any questions? Right, so now we're going to compute the inner product between these two Fourier transform. Okay, hopefully that can be a bit easier. So basically, so in this case, so we can just do the integral of this multiply that, right? So when we use this multiply that, and what do we got? Right, we have 4 terms, right? So basically we have like m f plus minus fc times delta f plus minus fc, right? So I just write it in a simple way to save time. So we have 4 terms, right? So it's f plus fc times delta f plus fc, and also same thing times delta f minus fc, and so on. We have 4 terms here, okay? And so in front, so we have the multiplication of the coefficients of a over 4 in front. Okay, so this is basically the inner product, right? And okay, so now let's do this integral, right? So now we have something multiply a delta signal and then do an integral, right? Here again, we're going to use the sampling property of the delta signal. Okay, so you're going to have some exercise in your homework 2 on this property. So yeah, let's see what we got. Remember that we have 4 terms, right? So when we multiply a signal with the delta signal and then do the integral, what do we got? Yeah, for example, let's see. So if I just have f minus fc, and here is f minus fc. Oh, sorry. Let's see. So if I have these 2 terms only, so what do we got? What do we get? So remember, so what we do is that we just plug FC into this guy, right? That's how it works. But remember, let's maybe write it down. But in general, let's say if we do an integral of, let's say, maybe a function, let's say x of f times delta f minus fc, right? Let's say df, yeah, it's df, right? What do we get? We have x of fc, right? We just need to plug this guy in here, and then that will be the result. Okay, so for this term, right, if we do this, we plug fc in here, what do we get? I mean, just fc, not minus. M0, right? So now if I have like 2 plus here, what do we get? 2fc, right? So since we have 4 terms here, so basically what we're going to get is we have f2fc, m2fc, add m0 2 times, right? Because we have 2 cases where this guy can be 0. And then we have add m minus 2fc. Does that sound reasonable? Right, I have 4 terms here, so that's basically the result. So now it looks much better than before, right? So now let's determine the value of it, right? So first, what is M0? It's a signal at 0 frequency. So what does that mean? DC. Yeah, DC component, right? So it's basically that. If you write the Fourier transform, so that is exactly what we do, right? Because we just put the complex exponential with f equal to 0. Okay, so that's exactly what you're doing there. So basically, for DC component, we just have yeah, maybe let's just write the DC component for now. Okay, but it'll be equal to 0 later. But what is this guy? I have 2 MC. Okay, so yeah, let's maybe I didn't describe the signal in very detail before, so because of the time limit in the last lecture. So we consider MF is something like this. Okay, and let's consider here the bandwidth. All right, and now after modulation, so we consider something like this, right? So for modulation, we want to shift it to a little bit far, right? We don't want any overlap in between. So basically, this is what we do. We shift it to a frequency component like this. So here is FC. Here is minus FC, right? So this is basically what we do. OK? Does that make sense? Right? So see, what is the condition here? So basically, here is FC. So this point is FC plus B. And this point is FC minus B, right? Because total bandwidth here is 2B, right? So we need to make sure this guy is bigger than 0 to make sure there's no overlap in between, right? So this basically means that FC has to be bigger than B, right? So, OK, FC is bigger than B, right? So what does that mean? So FC is bigger than B. So basically means that this guy is less than 2FC, right? Because B is less than FC, right? FC plus something is less than FC, so this is less than 2FC. OK, so if this guy is less than 2FC, now we're going to evaluate this guy at 2FC. So what do we get? Yes?
Is it still 0 then?
Exactly, right? So because so if we evaluate this guy, we need to evaluate this guy, right? So if we evaluate this guy at 2FC, so basically we're going to get 0. Does that make sense? Yeah, so basically this guy will be equal to 0. And similarly, if we do that at minus 2FC, so that will be 0 again. OK, and the DC component equal to 0. So everything is 0 in this case. Yeah, so basically, yeah, what your guess is correct. So this guy is 0. But so it's not that obvious to compute it from the time domain. So it will be much easier to compute it in the frequency domain. So finish computing this term, right? And then, so basically we have a very nice observation here, right? So basically it means, so this guy, the carrier component, and the signal component. So if we defined this before, right? If the inner product between this guy is 0, so it's called orthogonal, right? So basically it means the carrier and this, they are orthogonal. Okay, so which is very nice. Okay, great. So now let's compute the last one, right? The last one I think is yeah, the last one is this one, right? Okay, okay, just memorize this one, so I will write it here. So basically, again, we're going to use compute that in the frequency domain, so that will be easier. Right, yeah, maybe let me write it down again. So, okay, so again, so norm basically means the inner product between this and itself, right? So basically, we can convert it. Yeah, so this is exactly the Parseval's theorem, right? The power in the time domain will equals to whatever exists in the frequency, either it's power or energy. Okay, so basically, we're going to write the Fourier transform of this guy, which is half mf plus fc at half m minus fc. Okay, very good. Yeah, and now, so this is the norm again, right? So we can write it out as before. So in this case, so we have 1/4 of the first term. And then we have inner product, right? So it's inner product, so that is half times and 2, it should be half f minus fc, f plus fc. Right, and then we add the last term, so that is 1/4 again, f minus fc. Okay, very good. Okay, so now let's see. So what about this term? So what's the product of this term? The inner product of these two? You remember, so this is our signal, right? So this is our m f minus fc, and this is our m f plus fc, right? So there's no overlap between them. So it basically means that, so this inner product will be equals to 0, right? Very good. Okay, and what is that? So it's just the power or the energy of the original signal, right? So, or because in the frequency domain, so probably that will be the energy in the frequency, but the meaning of it is still the power in time, or the energy in time, whatever, right? So basically, yeah, because we have this, so that is obviously a power signal, right? So that will give you the power in time, okay? So then, so this and both of them, because just the shifting, right, it will not change the power and energy of the signal. So both of them will just equals to this guy, right? And now, so we have 1/4 in front, then now we have 1/2 here, right? So this is basically what we have, and that also equals to 1/2 mt, right? Okay, so that's the power of m. Okay, so let's give a notation here. So the power of m, we use Pm to denote it. Then this guy will give you Pm/2. Okay. Okay, so now let's compute PS, right? So what is the total power here? So hopefully still remember that we have 3 components here. right? The first component is power of the carrier, and then we have inner product, that's 0, and then we have this third component, right? So the total power would be the power of the first one, the power of the energy, or the power of the carrier, and add the power of this guy, right? Because the inner product is 0, so that's PS over 2, right? That's the total power, and this is the signal power, right? Given this, we could compute power efficiency as nothing but PS over 2 divided by A squared over 2 plus PS over 2, right? And this will give you PS divided by A squared plus PS, right? So this is the power efficiency for the AM signal. Okay, and then we need to multiply by 100%. Okay?
Are the two PS in that equation, are they the same?
Say again?
Is
The PS?
PS over 2 supposed to be PM over 2, or is that the same?
Oh, sorry. It's a typo. Yeah, PM, right? Not PS. Yeah, here's PS. Very good. This is PM. Okay, great. Any questions? Yes, quite complicated. So, but the result is relatively simple. Okay, so now let's see an example here. So consider example of tone modulation. So basically by tone, we mean that m of t is just a cosine, right? Cosine will only have one frequency. We call that as a tone, right? So basically in this case, consider mt is, we have equal to mu times a cosine omega mt, right? Okay, so here are a few parameters. So because that is a signal, right? So this omega m, so that is typically much less than omega c, right? So now our signal is just a cosine, right? And yeah, for this mu, anybody still remember this notation? So we mentioned that in the beginning of our class in the slides. What is that? Right. So that is called modulation index, right? That's equals to what? A over, oh no, MP over A, right? MP over A, right? So if MP equals to A, we say it's 100% modulated. If MP is bigger than A, we say it's over-modulated, which is not good. Yeah, anybody recall this? Yes, the modulation index, okay? So consider this kind of signal. Now, given this, let's compute what is the power efficiency here, right? So basically, we have A here, right? And oh, by the way, so this A is nothing but the amplitude of the carrier, right? It's the same A as before, same A as here. So in order to compute eta, so that is equal to PM over A squared plus PM, right? So we just need to compute PM, right? PM is the power of M, right? So what is PM here? Right, because it's just this constant multiplied cosine, right? So this PM is nothing but just mu A, the amplitude square over 2, right? Hopefully you can still know how to compute it. And so that equals to mu square A square over 2, right? And so now let's compute the eta. So basically eta here equals to mu square A square over 2 divided by A square plus mu square A square over 2, right? If we simplify this a little bit, so we can cancel all the A's here, right? And that'll be equals to, and then we multiply 2 on the numerator and the denominator. So basically we got mu square over 2 plus mu square, right? It's only a function of the modulation index. Okay, so this is basically what we got. Okay, it's power efficiency. Okay, as we know, right, so mu is normally less than 1, right? If mu is bigger than 1, so that's not what we want, right? So you can see it's an increasing function. The power efficiency is an increasing function of mu, right? So the highest number of it is when mu equals to 1, and the eta in this case is basically equals to 1/3, or 33%, right? So that's the power efficiency for the tone modulation. So is this number good? Is that what you want? Power efficiency only like 33%, right? So it's pretty bad, very bad. And that's the best possible you can get using this modulation technique. Okay, pretty bad, right? But in practice, we still use it, right? We use AM even today. Is that right? Okay. So now the question is, why still want to use it? Because it's so power inefficient.
It's really easy to demodulate.
Exactly. Yeah. Do you know how to demodulate it? Okay, good. It seems that you know everything. So yeah, it's easy. The reason we still using that today is the demodulation. So that is very easy. Okay, let's see how we can demodulate it. So anybody still remember? So why we want to use AM, right? So we introduced the DSC, so DSB-SC, right? So if we don't transmit a carrier, we can still demodulate, right? So why we don't want to use it? Yeah, we discussed the reason last time. Anybody recall? So why we don't want to use DSB-SC?
Because then we don't know the phase.
Very good. Exactly, right? So if we don't transmit a carrier, then we need to somehow generate the carrier locally, right? If we generate the carrier locally, then it's very hard, or it's relatively hard to make, to know the phase of the original signal, right? To synchronize it. Okay, that's why, we need, so that is called coherent demodulation, right? So if that is hard, then we want to have kind of like non-coherent demodulation, right? So here, the demodulation we're using here is non-coherent demodulation. So basically means that we don't need to know the phase, right? We can still do the demodulation. Let's see how we can do that. So basically, we have a few ways to do that. The first way is called square demodulation. Okay? So basically, it means that we only need to do a square to demodulate it, right? Let's see how we can do that in this case, okay? So let's remember that our ST is equals to, so STAM, right? So that basically equals to A plus this guy multiply cosine 2 pi FCT or omega t, whatever. Okay, so now what we're going to do is that we're going to square it to see whether we can demodulate it. I just square it, right? So basically, it means that if we have our signal as an input here, so basically we have a module here, so that do a square operation, and then we have some output. Okay, so we're going to see how this signal look like. Okay, and we don't consider any noise, right? Still, so this is what we transmit. We assume the received signal is exactly the same as what we transmitted. Okay, let's see how we can do that. So basically, in this case, we have A plus MT square and cosine 2 pi FCT square. Very good, right? So when we see something like that, we like it, right? So hopefully you'll agree with it, right? We don't like cosine because we don't know how to deal with it, except transforming it to the frequency domain, right? But now, if it's cosine square, then we may be able to do it. So basically, what we got here is this guy. And then we use the trig identity here, so we need to have a 2 here, and then it's 1 plus cosine 4 pi FCT. Okay? So now are you happy with this? So can we use something we learned before now, so far, to get empty out? Right, so normally when we have this, so we're pretty happy, right? So we can use the low-pass filter to filter this guy out, right? That can be taken care of by a LPF, low-pass filter. And then after that, we have this component. So we have this, right? Is that enough to know MT? Why not? Oh, we know. Yeah, let's assume that. Or if we don't know A is, it doesn't matter. So it's very easy to build a circuit to get rid of the DC component. Yeah, so A is not a big deal. That enough? Yeah, probably yes, right? It's like we know M squared, we know M, right? We can build a circuit to do the square root operation. Okay, like we have a circuit to do a square operation, then we can do a square root operation. Okay, then we're done, right? So that's basically the idea. Yeah, that's simple. Yeah, I think it's simple, right? So I don't know how to exactly implement that, but in the book it says it's simple. Then I guess it is true, right? Okay, so now it's pretty simple, right? But what is the loss here? So do we lose anything? It seems that's pretty straightforward, right? It's like the coherent demodulation, right? For the coherent demodulation, so what we do is that we multiply another cosine here, right? And then we have something like this, and then we pass the signal through a low-pass filter, right? Supposedly, we don't transmit, we don't know this guy exactly, right? By doing this, what are the loss? So where did we lose? Yeah, the problem is again this square, right? The problem is still this square. Okay. In other words, let me ask you one question. To design the LPF, what is the bandwidth for the LPF? How wide should be the LPF is? Should be the LPF? Say again? FC? Oh, FC is a carrier frequency. Yeah, I mean, yeah, I remove it. Yeah, maybe I'll draw this again. So basically, let's assume M, capital M of F is something like that. So we have the bandwidth is B, right? So if we have the DSP, yeah.
Shouldn't it be twice the bandwidth of the message signal?
Exactly, yeah, this is the answer, right? So basically, we have MT square here, right? MT square basically means that in the time domain, it's MT times MT. Then in the frequency, so that'll be like, it should be the notation. In the frequency, it should be MF convolutes MF, right? The bandwidth will be doubled, right? So basically, for this guy, the bandwidth would be doubled, right? So it would be 2B, right? Then the bandwidth of the LPF would still be 2B to filter this out, right? So this is where we lost. So we'll have a negative impact on this. Okay, so to summarize, so basically, let's see the entire procedure of the demodulation for the square demodulator. So basically, for the square demodulator, what we do is as follows. So we have our signal as AM input of T. Okay, and then we do a square operation first. So that's not a linear operation, okay? Then we pass that through LPF with bandwidth of 2B, right? And then we have a signal here after LPF. So basically what we have is something like this. We have, let's say we have an ideal LPF, and we have this guy here. No, should be, the square is only upstairs. Right, so we have, we have two there, it's upstairs. Okay, and after that, so we're gonna do a square root operation. right? And after square root operation, what we got is this guy over square root. Okay, and then we need a DC blocker, so we get rid of DC component. Okay, and then we just multiply this guy by, so after DC component, then we'll have this, right? And then we just need to multiply by square root 2, and then we get our empty out, right? So this is the entire demodulation process, right? So, and we don't need yeah, never mind. So yeah, that'll be it. Okay. Yeah.
So when you were talking about like the loss, because the low pass filter is 2 times the bandwidth.
Yeah, it's not the loss. It's basically, so we need something better, right? So LPF, the bandwidth of the LPF have to be wider.
Okay.
Yeah. So that's supposedly to be harder to do. Oh, by the way, so I checked a little bit. So in the last lecture, so you have a question on this Butterworth filter, right? So which has a nonlinear phase, right? So that is not good. It's a distortion, right? So in practice, so normally we can recover it by many approaches, right? So basically for Butterworth filter, so the most distortion happened in the cutoff frequency, right? So one way to deal with that is to make the low-pass filter a little bit wider, you know. But if we make that a little bit wider, you know, there may be other problems, right? But in that case, at least we can get rid of the phase distortion problem, right? Or, you know, we can somehow reverse this distortion. Okay, for example, I think what we can do is that, you know, after passing through this Butterworth filter with a nonlinear phase distortion, and then you correct it by passing it through a all-pass filter, meaning that in the magnitude it's all one, but there's some phase, you know, operation going on to reverse this operation. Right? There are many ways to deal with that, but that is a problem for Butterworth filter, right? Remember, think about it, right? If in the frequency domain we have a nonlinear phase, so in the time domain it basically means that we have a nonlinear shift. The signal shifts around in a bad way, right? So we need to correct it somehow. Okay, so yeah, we're out of time. So next lecture, I'm going to very briefly talk about another demodulator for an AM signal. And then, so we're going to talk about bandwidth efficient modulation. Okay, thank you.